I'm Carl Anthony, Managing Editor of AutoVision News, and welcome to AutoSens Insights. We are joined today by Erick Parra, the Business Development Director of Technica Engineering. And Erick, welcome to the program. So good to have you here today.
Thank you. Thank you very much, Carl. It's a pleasure. Thanks for having me.
So Erick, let's start at the beginning. Tell us a little bit about Technica Engineering. Give us an overview of the company.
All right. Well, thanks for the question. Technica Engineering is a young, middle-sized company in Germany, Munich, Germany. We're founded 2008. I have, in fact, a small promotional video that I would like to share with you guys if you can see it. It's a very short video then.
We are Technica Engineering. We assist automobile manufacturers and their suppliers with development and testing projects for the validation of vehicle technology systems. We thereby use our own hardware and software solutions. We offer our clients an all-in-one solution design, supporting the innovation process from problem analysis to solution and validation. We provide cutting-edge technology, develop and manufacture our own products to the global market, creating the automotive future.
Erick, thank you for sharing the video. And so I want to get into a lot of stuff here after we've seen the video, and I know our AutoSens viewers are also excited to learn more. But let's start at the beginning. So how did the introduction of Ethernet happen in the automotive world, and then what role did Technica play in?
Yeah, those are excellent questions, Carl, because they highlight pretty much the spirit of Technica Engineering itself. So the automotive world has been experimenting with communication technologies for a long time, as you know. Like around about the 80s, CAN, Controller Area Network, came into being. And we were just pretty much at the right time, in the right moment. So that's the Technica Engineering part. It was 2008 in Munich. And we were working for BMW. And BMW, maybe this is known as well, invested a lot in developing technologies for communication for a long time. They introduced FlexRay. Later on, they introduced MOST. And then they came at a point in time in which they were having 7 series models, that was back in 2004, to be launched in 2008, that would have for the first time navigation systems. It has nothing to do with ADAS, but it has to do with infotainment and, let's say, introduction of technology into the car. And the issue that they had here was that they had to reprogram, we call this flashing as generally in the technology world, they had to reprogram the electric control units at the end of the production line. And they knew that the only interface that they had to do this was CAN over the OBD connector. And the amount of data to be flashed was round about a gigabyte, let's say, roundabout. And it would have taken like 15 hours to happen. So the production itself of the car would probably take as long. And then imagine just waiting again 15 hours for every car to reprogram the whole thing. So this is where Ethernet came into play. It was done by a guy called Thomas Koenigseder. He was at BMW, the technical director, the group leader to do this in the infotainment side and in the networking side. He searched for a high bandwidth technology that would be able to be fitted on the OBD connector. They would have access to all the ECUs in the car and would be able to transmit this data really quickly. And the BMW chose strategically an open protocol, let's say something that is multi-sourced and that's widely used, and this is Ethernet. So for the very first time, they used fast Ethernet, standard Ethernet, which was standard at the time, 100 megabit per second, and they introduced it into a so-called central OBD gateway. And this device has the task to make a routing, let's say, of the information from the outside world into the car, and then to transmit at very high bandwidth the flash information. So to put it in a general way, because of course there's more technical details to make that happen. And this was successful. And the 2008 launch of this 7 series was successful. And that's what Technica Engineering was founded, 2008. And that's what I said, that we were at the right moment, at the right time, in the right place. because management wanted to use this technology in the car. But it wasn't as easy because this technology is built for desktop, for laptops. So you don't have an EMC performance, let's say a character of the electromagnetic emissions that has to be very robust, like in the car. And that technology uses wave shapes that are so square that they generate a lot of EMC, and they disturb the flex ray and the CAN communication, which is already in the car. So that's something you cannot have. So to solve that, you could do very heavy shielding, which is doable, but it's expensive. It's something the automotive industry cannot have. So Thomas Koenigsegg started looking for solutions in the market, and he asked for all the silicon providers, and they laughed at him. They said, you cannot do that. You cannot have that Ethernet technology, 100 megabit per second, full duplex on cable type that would be suitable for the world, for the automotive world. And only Broadcom answered that his question, and they had a different kind of technology, was called broader reach, which was done for cheap internet for the World Wide Web in Southeast Asia. And they said, okay, we can adapt this for the automotive world for you. And Technica was the engineering provider to build a PCB with this solution and to do the evaluation, the electrical parameters and everything to make sure that this would work. And that's where it all started, with the, let's say, Automotive Ethernet and Technica Engineering.
So Eric, I have more questions, but I just want to say that I love that story with the BMW. I love BMW cars. I know a lot of our viewers do too, but I didn't realize. So you came out of that. I remember the 2008 7 Series. I remember that car.
Yeah, it's a pretty nice car. Yeah.
So
what can I say?
So now, so this leads me. So we have Technica as an engineering company doing this incredible work with BMW, but how did you go from an engineering company to a product provider? And that's something I know our viewers will be curious about. How did that happen?
Yeah, that's in fact a pretty good question. I've got in the slides that I provided, there's an overview of the different generations of products that we built. You can check it out. So it's a little bit complicated, but you can see on the very far left side, we've got the evaluation board of broader reach. And as you correctly said, we are an engineering company, and we were doing that heavy electronic-based development and work. And in parallel, we were doing consulting work. We were doing test execution of the ECUs that already have Ethernet. And that's a little bit difficult to do. That's where we come from. We come from the electronics development engineering side, and in parallel doing consulting and test execution. So we were designing test benches, looking out for tools which we could fit into our test benches so that our engineers could design tests and could actually execute them. So you have an electrical control unit that has all of these interfaces, and you need to interact with it in order to do a test case. So you have to put it in a set as if it was inside the car, so interacting with other devices. So you need to have interfaces. And simply said, there were no such interfaces at all in the market. And we already had the technology and knew how to do it. So we built an evaluation platform, converter, which is pretty much the first product that we had in order to do a point-to-point conversion between fast Ethernet, which is in the computer, where you can use it with your tools and everything. And then this new thing, which is a single pair Ethernet that goes to the ECU. And later on, of course, that is just a very basic thing to do. We were the first on the market with it. 2010, we launched the first converters to the market because there was nobody else doing it. So it was like kind of close. We have the electronics development, we can package it, and then sell it if somebody wants to buy it. And the tier ones, of course, outside of the BMW spectrum needed it. So they started buying it, it started going good. And later on, we had to develop something to test the device itself. So you know that Ethernet is a point-to-point connection. It's not a bus system like FlexRay or CAN or something like that. So you're going to need some kind of test development, test environment that enables you to do a test access point. We know it from the telecommunications world, but it did not exist for what was back then called broader reach. So we built this, and we did it with a Vulkan switch from Broadcom, which is not automotive grade. When you're working with Ethernet, I know the audience some of them might be familiar with it, some of them might not be familiar with it, but Ethernet is a point-to-point connection technology, and you need something like a switch, which is a smart microprocessor-based device with multiple ports and buffers and a smart scheduler, and even an ARL table, so-called ARL table, so address resolution table, which is capable of identifying when messages come in, they go into the buffer, and then the switch looks, well, where is it supposed to go to? And what port am I supposed to send it to? And the switch itself enables then the single devices that are connected to it to send data to each other. You can put switch after switch after switch, and then you can make a big network. And if you want to separate data from going from several ports, there are things called VLANs, virtual LANs. And it was very important to start working with these kind of things, because if you capture the traffic from the device itself that you're testing, and it goes through a switch that is your switch, then the device itself starts hearing itself, and it's going to cause a lockdown, right? So you need to work with things like VLANs. This was completely new in our industry. So we enabled our test system to do this. And we saw that it worked, but then we also saw we needed more ports, we needed more automotive grade stuff. So we created the so-called media switch. And this was really important because this pretty much set the stage for the very first measurement technology available at all to test the future generation systems at BMW, which was in that case the BMW X5 from 2015, which had for the very first time a surround view camera system with Ethernet. By the way, Technica Engineering also built the first prototypes for those cameras. So the world's first ECU, if you want, is a product from Technica Engineering. So that takes us to having working test solutions that we effectively could use in our products, in our projects, and that the market needed. So we started selling them, and yeah, nobody else ran. In fact, all the competitors, all the tool vendors that you know that produce test systems for the cars started evaluating the technology in 2013. By that time, we had 5 years experience and already several generations of products on the market working. So products was, let's say, not the focus of Technica Engineering. It was until, say, 2016, 2017 that it started becoming a relevant part of our company. And today it's more than a third of our revenue. So now we're happy to say we're proud product providers for the automotive world as well.
So Erick, just as you're talking here, I go back to this incredible experience with BMWs, from these cars in the manufacturing facility to getting them on the road. What a wealth of experience there. You're an engineering company, you're a product provider. So what I think is, I think a lot of our AutoSens viewers, I think they would want to hear your thoughts and insights then. What are some of the biggest challenges when it comes to testing autonomous driving systems based on your experience?
Yeah, pretty good question, Carl. So this takes us on the, let's say, the red path of the things that I've been talking about, very fast forward to where we're now. Because, I said BMW X5 2015, that's wrong. It was 2013, the SOP. Because in 2015, for the first time, BMW launched a full architecture of autonomous driving systems, of ADAS systems, already working with automotive Ethernet. Yeah, so that's where Technica Engineering starts gathering information on how to test ADAS systems. And right now we are providing full test benches for the central computing platforms that execute the ADAS functions themselves, and we're testing that. So there's a wealth of experience in Technica Engineering and the testing side as well, for specifically for the ADAS area. And I believe that testing ADAS systems is probably the most complex technological area in the automotive industry at the moment, because you have this huge amount of interrelations, and you have this very high level of complexity. So let's take it down to the different elements of what I would say what's the most difficult part. So first of all, you've got a lot of sensors, which are the electrical control units and electrical devices that via infrared sensor information or ultrasound or visual cameras, they are giving you information of what is surrounding the car. And then you need to work on that information. So you need to make yourself a digital map of what is happening around the car, and with dynamic, the capacity to do dynamic operations where the car is going to. So what is your steering angle? What is your rate of acceleration? What is your rate of braking? Everybody in this area is very familiar with that. And then, of course, you need to translate that into a logic of, am I supposed to do something as a car, as a function, and then execute autonomously braking functions, accelerating functions, steering functions. So I would say that there are many super difficult parts for testing this, but one of the most difficult or one of the greatest challenges is the time synchronization between devices themselves. It's a challenge to have a very good developed system that has it. And then when testing, it's a huge challenge not to break that time synchronization when you are actually gathering the information that comes between the devices, and the devices are synchronized to each other. Now you're introducing your measurement device in there, like you're watching, and not to break that time synchronization. That's a huge aspect, right? Especially because, as I said before, Ethernet is a point-to-point connection. Now, the logical consequence of Ethernet being a point-to-point connection is, if you want to sniff the information that's going between two devices, Ethernet devices, let's say a radar and a central ECU that are sending information via Ethernet, or a LiDAR system, or different sensors use different solutions for communication. If it's Ethernet, for example, you are going to have to break that line to cut it in the test car. You have to effectively go to the cable harness and cut that line and put a tap in between. So you put a tap from Technica Engineering, for instance. We've got this huge experience in knowing how to work with that. And we know that the link stability of the Ethernet links has to be super precise. You cannot have a device there that is going to give you link instability, which in return would make the communication break between the sensor itself and the measurement device, then from the measurement device to the sensor again, right? So the link stability is super important. And then Ethernet packets, Ethernet frames, they have a certain length. Now, today we've got more than 100 base T1, more 100 megabit per second. We've got gigabit as well, so 1000 base T1. So you're sending data with the gigabit. So this means that in the gigabit time, you need 1 nanosecond to send 1 bit. And in the 100 base T1, you need 10 nanoseconds to send 1 bit. In Ethernet frames, they go from 64 byte to 1500 byte. Now you have to break that down into bits. Now you multiply that by the time, and then the transmission time of your Ethernet packets, they can be between a couple of microseconds to more than 100 microseconds long. And all of that message has to be stored in the device, or go through the measurement device, and then arrive at its destination. So you have multiple strategies on how to test without breaking your time synchronization. You can use a time-aware switch, for example, or you can use a tap, a test access point, terminal access point, or a sniffer, or a spy, however you want to call it, that actually allows the data to go through without making a store and forward, without previously storing it before, and having a very deterministic delay that is always the same. So what happens when you have two devices that are electrical devices are connecting to each other, and you delay the time that sender and receiver receive their messages? And if it's the exact same delay for the device that is receiving, it looks like you're a little bit further away, but it's the exact same thing. It would be different if that delay jitters. Then the sender and the receiver, they notice that the messages come back and forth in different times, and the time synchronization get lost. So I would say that the capturing data among devices in the case of Ethernet without breaking the time synchronization is one challenge. But the next challenge is, you don't only have Ethernet. There's also FlexRay, there's also LIN, there's also CAN, there's also different kinds of serialization of SerDes technologies like LVDS and FPD-Link and so on. And all of these technologies are being used by the whole system. So you need the sensors, you need the computing engines, and then you need the actors. And when you capture the information of all of this in order to see what's going on while you're doing the test and evaluation of your individual systems, all of this has to be time synchronized to each other. And that, I would say, is part of the largest challenge. There's many, many more challenges. You have things like the devices themselves, they start up really quickly. and they start sending lots of data. How do you capture this data? You need special devices to capture that data. Now, these devices are going to be in your car. You're going to be running around the streets. You're going to be gathering data, which means they have to be inside the car. They have to start up and shut down with the car, because otherwise, if they keep on running while your test driver is asleep in the hotel, they drain the battery, and when the test driver comes out, then the battery is dead, right? So these systems are Linux-based systems, for example. They have a very large boot up time. So when the test starts, you're capturing your logging storage system is not yet ready to capture the traffic that goes between the ECUs. And if you lose that traffic, that's the most relevant traffic to establish the sessions with the devices, to open the sockets, to register the services that are running out there. If you lose that traffic, you lost the most important traffic. So that, I would say, is the third largest challenge of when doing tests of autonomous driving systems. To have time synchronization, to have fast boot up time, and not to lose the data at the very beginning. There's multiple, of course. When you go to the function tests themselves, you have to make sure that the data is in a format that is usable for the tool chain that analyzes the data and that computes it. And then you have that's something that's outside of the scope of technical engineering. When you start looking at the functions themselves and the data mapping themselves, you're going to have tons of data. You don't want to see everything. You just want to see things when they happen at a special point in time. So there's other solutions to do that. But all the things that I mentioned before in terms of gathering the data, making sure it's time synchronized, making sure you don't lose the initial data, all these kind of things, that's where Technica specializes in. It also, that's what I would say are pretty big challenges when testing ADAS systems in a car.
Erick, this is incredible information and incredible depth. I mean, yes, the video that you had and the slides that you've given us today, but just in your descriptions, I think our viewers, many of who are engineers themselves, many who are vehicle perception technology managers, they're involved in ADAS every day. I think that they are really going to appreciate that level of depth when it comes to these challenges, particularly these challenges that maybe we didn't think about 4 or 5 years ago, right? So I think that the next most logical question then, Erick, is, what is your view on format and tooling then? And how do you use that to accelerate technological development?
Yeah, so that's also a very relevant question, because it's one thing is you manage your physical layer and you understand how your CAN, your LIN, your flexor, your Ethernet, your SerDes work. You have solutions to capture that data and put it onto your logging systems, and then you put it somewhere it needs to be analyzed. Now, the issue that we have seen here, and our take on that on Technica Engineering, is we had to evaluate test solutions at our very early stage. How do we work with Ethernet? It's a very different story to have 100 megabit per second, have 100 million bit of data that comes suddenly in a test system, when before in the automotive world, it was all CAN and LIN. It's the fastest you can go with CAN in a real system is 500K, although there's in theory you can go a little bit faster, but usually you use 250K, 250,000 bits per second at the most, and you're getting, making 10 or 20 of these in the car. But if you add it all together, you end up with a couple of megabit per second. Then FlexRay, I'll go a little bit faster, a couple of megabyte, and then megabit per second. And then most, of course, can do like 10 or so. And if you aggregate all of this, you're still doing peanuts, if I may say like that. You're still gathering only a few dozens, maybe, of megabit per second of data that comes from the car of systems that you want to test. I'm talking before the introduction of Ethernet. Now, 2015, when this with the first architecture goes out with ADAS and with infotainment and with telematics of BMW, by the time 2015 came, Volkswagen already had a couple of systems in the market with Automotive. In the big three, they were evaluating. I think GM was quite advanced on that. JLR was launching also a device on the market back then, 2015, with a few lines, and in the Asian market as well. But then we were talking about the most advanced architecture of using automotive Ethernet and really high bandwidth technologies like this was at BMW, and the aggregated data was just simply huge. Yeah. So now you need to do a complete shift of your tool chain. And what happens with toolchain, the solutions that you had for testing lin, can, and so on had special formats. So you don't have the same format for a CAN message than you have for a lin message or you have for a FlexRay message, because the payload sizes and the sizes of the messages, they are different. In a computer, for instance, cannot work with a CAN message that is only 3-bit long in its payload, and then a couple of bits more for header and CRC. So that means that when you put that CAN data on your computer, you need to change the format. Changing the format means you need to find some kind of solution to store that data, and then you need to have a tool chain that can access that format, so that and then can access also database information from the car manufacturers. So what does this format mean? What ECU does it come from? Where can I use it for? So there's a big, let's say, landscape that is completely heterogeneous, and it's totally a chaos if you look at it, and the world market of tooling, and everybody starts to use their own formatting. Right now you come to Ethernet, and suddenly the amount of data that you have explodes by tens or hundreds of times more, and all of these tool chain providers are kind of overwhelmed. And what do we do now? And hey, we want to stick to the things we've been doing for the last 20-30 years, but hey, now we have so much data, what do we do? So there's a strong trend in the automotive industry to have tool chain that goes in the open source side, and there's another one that goes in the proprietary side. And there are a couple of players in the proprietary side that have a really strong weight on the standardization organizations for formatting, like ASAM, for example. ASAM, ASAM is one of the big standardization organizations for formats, for data formats. And now you look at this big two poles, and so there's a very big, let's say, political play back there. What is more important, what is more relevant? And some of the proprietary ones want to stick to their proprietary format. So there are things like MDF, like BLF, and so on in the market that are hugely problematic when you have this huge amounts of data, because those formats, what you need to do is you need to get the raw data, the raw Ethernet frame. Every Ethernet frame is always the same. You have your destination MAC, your source MAC, your Ether type, payload, and CRC. It's always the same, right? And there are formats in the industry that have been around for decades, like the so-called PCAP, PCAP, right? Or now the new one, PCAP-NG. And those are used in the telecom industry, in the manufacturing industry, in the aerospace industry. Everywhere you use with Ethernet, you work with PCAP. There are very successful tools working with PCAP, like Wireshark, for example. We use it a lot in our projects. So some our car manufacturers have actually adopted these formats and can work with it, and it's really good. And then some others are strongly trying to go towards this old CAN, LIN, FlexRay based format. So my take on the question is that there's a very strong proprietary side, and it's problematic because to work with those formats, you have to dissect, like break down all of these messages, change endianness, change byte sizes, put it in different formats, and then you have to rebuild it all back, and you lose data. And every time that you do any kind of these data manipulation steps, you could do a mistake. And then you just imagine you're testing ADAS. When in the world are you going to find out that in your tool chain there was a format manipulation error that down the tool? It's going to take you months. How much does it cost to debug a mistake for months when you're talking about big tier ones here? You're talking about pure tier twos, pure OEMs. You're talking about 6-7 figures in wasted money just for searching these kind of things. So our take in formatting is you should stick to what works, and that's industrial standards, things like PCAP, and also working with Wireshark, open source. Wireshark, we're friends of Wireshark. There was a LinkedIn post from my friend Lars Fulka, Dr. Lars Fulka. He used also to be at BMW. He's also the inventor of one of the specific protocols that are used in the automotive industry called SOMIP. He published that the next generation Wireshark, I think it's 3.4, has a native support of a Technica Engineering protocol, Ethernet protocol, that we use on our measurement systems for ADAS, which are called the capture modules. So our take on this is the tooling industry should look at open standards. And open standards are going to take you faster and more reliably to a higher quality result when it comes to analysis of data.
Right. So Erick, after this interview, so let's say that our AutoSens viewers, perhaps they're curious to learn more. They have seen all of the depth and the slides, and just in your presentation alone, just the depth that you have given here and the context you have given. So let's say that our viewers, that they see all that and they say, I would like some more information. I would like to contact Technica Engineering and get some more information as a follow-up to this interview. Erick, how do our viewers go about doing that?
Yeah. All right. Thank you very much. So I would say our website has a lot of information of our products. It's www.technica-engineering.com. You will go to the English website like that. We're a German company, so there's also a .de domain. You go to the German language company. But of course, if you want to have something more personalized, we have a dedicated email address for customers who are interested in our products. They might want to have some guidance on which product is the right one for their application, which one is the right model, especially in the gigabit, automotive gigabit area. Because it's a very, very new technology, there are issues there with the different kinds of versions of the files that you use and so on. So there's a lot of questions on that. And the email address that I would recommend your viewers to use is technical sales, all together, like technical sales, at technica-engineering.de, for DE for Germany. They have a direct access to the colleagues in my team, and yeah, any kind of question they might want to ask, we're there for them. There's also well, we're now in Brussels, but we also have a representation in the United States. But in any case, any question that comes to technical sales at technicaengineering.de goes to the right place. There's also representatives of Technica Engineering in Asia, in Scandinavia. So yeah, viewers can just put their emails in their questions there. If they're in Europe, we'll take care of them in Munich directly.
Of course. Erick, we want to thank you for your time. Again, with AutoSens, we have always said that technical content is the focus. And so we always love getting into an interview where we go into this depth and this technical content. So we want to thank you for your time today, for sharing your expertise with us. We want to wish you the best of luck going forward. And we'll catch up with you here later on for the Detroit interview in just a little bit.
Yeah, awesome. Thank you very much for the opportunity, Carl.
We're speaking today with Erick Parra, the Business Development Director for Technica Engineering. For more great content from AutoSens, visit our hub or our YouTube channel. Just search AutoSens.